Hi everyone, this is my Physics Lab 3. So the purpose of part 1 of this lab was to find the mass of a black hole through analyzing the motion of a star. And the purpose of part 2 was to find the initial velocity of the spaceship so that it could orbit without crashing into the moon or planet. And so some details are we used the motion data to apply Newton's second law and the law of universal gravitation in order to analyze the orbit. And through this, we simulated how combined gravitational forces can affect motion and produce complex orbits. So here are the results of the lab. On the left, it shows the elliptical orbit of the star around the black hole. And in this case, the system is a star while the surroundings is the black hole, space, and other forces. And through this, we were able to understand how the direction and magnitude of the net force created the orbital motion. On the right shows on part 2 of the lab where the orbit of the spaceship around the moon and planet is shown. The system is a spaceship while the surrounding is the planet, moon, space, and other forces. And we were able to determine the spaceship's path under simultaneous influence of the planet and the moon. So here are some equations that we used. The first principle we used was Newton's second law, and it's composed of the position and velocity update formulas. The second one was universal gravitation, shown right there, where G is the gravitational constant, M's are the masses of the objects, R is the distance of the objects, and R hat is the unit vector. And the last column shows curve and motion formulas. This is used when an object is moving in circular motion. So curving motion has two components, which are the parallel net force and the perpendicular net force. And the formula for the parallel net force is the change in momentum divided by delta t times p hat. And this is the change in speed, or the magnitude. The formula for the perpendicular net force is mass times speed squared divided by the radius times n hat. And this is the change in direction. So this is the code for part 1. We were given the gravitational constant, the mass of the star, and delta t, and we had to find the initial and final momentum of the star, which was the star's mass times the initial and final velocities, and we used this to determine the change in momentum. We were then able to find dp dt, which is the net force, and we used that to find both the parallel and perpendicular forces. So finally, we were able to calculate the mass of the black hole, which is the magnitude of the net force times the distance squared divided by the gravitational constant times the mass of the star. And after running the code, we found that the average mass was 9.462 E33. So for part 2, this is my code. We were given the gravitational constant, the mass of the planet, moon, and ship, the delta t, and initial conditions of the moon. And I had to find the net force for the moon, and this was found by first finding the gravitational force between the planet and the moon and the ship and the moon. And once these values were found, I added them up to find the net force on the moon, and then finding the net force on the ship was basically the same process, just for those values. And then I used that net force for the moon and the ship to find their velocities. And then after completing the code, I went through trial and error to kind of find the initial velocity of the ship. And I concluded that it was 25,000 in both the x and y direction. And through using those values, my ship didn't crash. So some error could have been through the velocity calculation because it was kind of random. I did trial and error, so it's definitely possible to get better values for the initial velocity. And also within this, I didn't really account for other gravitational influences, so there could have definitely been something else within space that could have interacted with the ship. So what does this mean? Discuss how net force and its parallel and perpendicular components are different from the rate of change of momentum and its parallel and perpendicular components. So it's mathematically the same to calculate the parallel and perpendicular forces of the net force and the rate of change of momentum. So when calculating the net force, all of the external forces acting on the system must be accounted for. So when I calculate the rate of change of momentum, you only really need the system's change of momentum. So for the what if you wanted to predict the motion of the entire system, what would you need to include in your computational model, whether there be any dominant interactions or would they all contribute more or less equally? So all of the forces, the black hole, star, planet, and moon, would have to be accounted for, and we would have to find the net forces for each of these components. And due to its large mass, the black hole would not have the dominant interaction, but the distance could have an effect on the interaction. So that's it. Thank you.